Hi, welcome to the Point Set Topology 9th live session NPT course. This is Shovik. I'm third year scholar by the Metro of Environment Custody. So today it's the ninth session. So we are total till now, excluding this ninth session, there are total four sessions left. Okay. So today we shall start with by solving of some previous assignments, including subjective objective work. Okay. So first let me know that am I audible and the screen is visible to you. Please let me know. Please let me know, Avinash or Mustaq. Please let me know whether am I audible or is the screen visible to you. Okay. So 1 minute. So today we shall start with the assignment 5. So start assignment 5 with objective type question. Well, so let's solve the first problem. So let's solve the first problem. What it's telling show that so this true or false type of question. The statement is that the Q has Q instead of rationals has a house dot 1 point compactification. So suppose Q has a so it's true or false. So the Q has a house drop in 1 point compactification. So what will be the answer? So think about it. So what is the definition of 1 point compactification? And of which space the one-man compactification makes sense. If the space is locally compact, then only the word one-point compactification makes sense, right? But I've already seen that Q is not locally compact. So of course, Q does not have any one-point compactification. Okay, or basically, suppose let Q has 1 point compactification. Then call it Q. Suppose Q has one compactification, call it Q, call it Y. Then Y minus single point will be locally compact, right? But Due to one-way compact, this thing exactly equal to this similar to what? Q is locally compact, but it is not possible. You have proved this previously. Okay, so that's why Q is not so answer of this previous question is false. So this is false. Okay, now question number two. One. So the next question. So question homeom. So next question is the following. Homeomorphic compactifications are equivalent. Homeomorphic compactification equivalent. Okay. So what does this mean? Suppose a space X has two compactification X and Y. Okay. So uh, suppose a space has two compactifications. Suppose they're homeomorphic. Then equivalent this means what? We need to show here is this a map X and Y such that restricted to the original space that we guided. Okay, so such a thing is not possible. So for example, take so there is a counter example. Okay, take x equal to n, y is equal to 1 by n comma I is equal to 1, 2, and n belongs to union 0, 1, comma 0, dot. Now y being closed and bounded, subset of R2 is compact. Now we give two dense embeddings. This means what? Dense embedding H1 and H2 of X into Y, into Y, such that the compactifications Y comma H1 and Y comma H2 are not equivalent. One. Huh. So So the compactifications y h1 are not equivalent. Okay, but of course, uh, but of course, but both compactifications being space y will be homeomorphic. So for that world, for the counterexample, what we do, we'll define h1 n comma y given by h1 of huh. So h also we have what h1 we have defined a function h1 of 2n is equal to 1 by n comma 1 and h1 of 2n minus 1 is equal to 1 by n comma 2 for all n belongs to n. Okay, now consider h23n is equal to 1 by n comma 2 for all n belongs to n, and h2m is equal to 1 by n comma 1 for all n not equal to n. Now claim is that there does not exist any homeomorphism F from Y to Y such that F compose H1 is equal to F compose H2. Okay, so suppose if such a homeomorphism exists, then what we'll get, if such a homeomorphism exists with F compose H1 H2, then H1 of 2n to 0 comma 1, and so f of h1 of 2n f of 0 comma 1. However, that is such a situation not possible because if we consider subsequence h of 2n has two subsequences converging to different points. Therefore, f is not continuous at all. Hello. So that is the argument. Well, so let me know till now, do you have any question or confusion? Well, so since okay, so it seems that it's clear to all of you. So well, so now, let's move on to the next question. One minute. Well, now let's move on to the next question. Okay, the number of closed subalgebras are three that are one-dimensional subspace is option A 3, option B 7, option C 8, option D 27. What is the closed subalgebra first way? Closed subalgebra is a subgroup which satisfies the basic multiplication addition property. Okay. Now the question: how many closed one-dimensional subalgebras? Of course, the closed one-dimensional are of course some kind of subspaces. Okay. So the argument goes as follows. Okay. So let me tell you clearly that this let me tell you clearly that this argument, yeah, this argument is quite tricky. Okay, it is not direct. So let me show the argument. Okay, so let W be a one-dimensional closed subalgebra of R3, and suppose ABC is its basis. Then, of course, due to subalgebra formula that ABC whole square should be equal to A square, B square, C square. W. Thus, for some lambda belongs to R, we must have A square, B square, C square is lambda times of A, B, C. And this gives A square lambda A, B square equal lambda B, C square lambda C. Okay. Now note that W is one dimensional. Not all ABC equal to 0. So where the following cases. What are the cases? First one is A equal to 0, B equal to 0, C not 0. In this case, the subalgebra will get 0, 0, 1. Option 2, A equal to 0, B not equal to 0, C equal to 0. Subalgebra which will get will be 0, 1, 0. Option 3, A not equal to 0, B equal to 0, C equal to 0. The subalgebra will get 1, 0, 0. Option D, A equal to 0, B not equal to 0, C not equal to 0. We will get B equal to C equal to lambda, and when it is about 0, 0, sorry, 0, 1, 1. Okay. Of E will be A not equal to 0, B equal to 0, C not equal to 0. So we will get A is equal to C equal to lambda, and so we will get subalgebra 1, 0, 1 generated by this thing. For we will get A not equal to 0, B not equal to 0, C equal to 0. In this we will get A equal to B equal to lambda, and we will get a solve generated by 1, 1, 0. A not equal to 0, B not equal to 0, C not equal. In this we will get solve generated A is equal to B equal to C equal to lambda, and we will get solve generated 1, 1. one. Okay. Well. So well. So there is some issue with my camera. So let me um, close the session. I shall rejoin the session. Okay. Sorry for the inconvenience. Hi. Sorry for the inconvenience. There is some technical issue. That's what I'm trying to fix by myself. Now the issue has been fixed. So now let's get back to our original discussion. So of course, since 1 minute. So since so of course, so so finally the 10-minute session. So there will be 10 extra session because this has not been completed fully. Okay. So yeah. So can anybody confirm whether I'm audible or this can visible to you? Uh, can you please confirm whether I'm audible or is this screen visible to you? Can you please confirm whether I'm audible and its screen is visible to you? Okay, I think so. Well, so now let's go back to the original question. Huh. So what was the original question? Yeah. So the question is that so initially we're trying to show that under the condition, namely where so there are some certain condition. The final condition A not equal to zero, B not C not equal to zero, A B is equal to lambda. Okay. So the condition H is what? Uh, so okay, so all possible seven conditions has a row. So these are the only possible one dimensional subalgebras of R3. Okay. So there are total seven subalgebras of R3 of dimension one. Okay. So there is total seven subalgebras of dimension one. Okay. Now so now go back to the next question. Go to the next question. So instrument goes as follows. So let x equal to c of minus pi comma pi. Then
Hello, sir.
yeah, please tell me.
Can you repeat the group number 3?
Well, yeah, sure. So in proof num so in the in the uh, so in the question number 3, what we want to do, we want to find all possible closed subalgebras of R3 which are one dimensional. Okay, so for that we need so basically for that we need to find all possible bases, or at least how we need to understand how these subalgebras will be generated, right? So suppose W is the one dimensional closed subalgebra of R3. Okay, and suppose ABC is the basis. Then due to subalgebra criteria, this equation holds, that is a square b square c square is equal to abc whole square. Okay, now since this holds, this implies by linearity we will get what, we will get some lambda for which such a condition will hold. Now using, so this implies what, a square equal to lambda b square lambda c square lambda. Now using this abc, using this equation we can find total 7 possible ABC and total 7 possible ABC in terms of lambda. So basically we are getting total 7 different generator by which the subalgebra might be generated. Okay, so that's why total 7 is answered. Okay, do you understand? And basically you need to find the solution of the system of equation a square lambda a b square lambda b c square lambda c. You need to find the solution, the number solution of this, then you will get the answer. There is nothing complicated really. You understand? Do you understand?
Yes, yes.
Oh, one. Well, so now let's go back to the next. Okay, so let's go back to the original question. The original question is what? Huh. Suppose x equal to c, then the set of all continuous functions from minus pi to pi to r, and consider v is equal to L of fn all with x, such that fn x is equal to sin nx. The vector subspace spanned by all sin nx. Then he is then subset of x with respect to infinite down. Okay, so how to do this? So firstly the answer is false. So what is the counter argument? So take any element of V. It satisfies the condition of what? It satisfies f of x is equal to minus f minus x for all x belongs to minus pi to pi. Okay, so this implies what? The function fn goes to f and fn goes to b, and then taking limit on both sides, we get what? F of x is equal to minus f minus x. Okay, so so but there exists many element in x which are not odd. For example, constant function 1. Okay, so that is the argument. So now the next question. What? Oh, so now the next question is the following. So the question is then which of the following maps are proper? Which of the following maps are proper? So the options are given as follows. The inclusion map, open 01, close 01. Again the inclusion map, open 01 to R. The function f r to r given by f1x is equal to 1 x squared. Option D, f2 r2 to r with f2 x comma y is equal to 1 plus x. Option E, f3 r2 to r with x comma y equals to x4 to y4. Option D, the function g with r2 to r one. The function g dot to r given by g1 of xi xy is equal to x comma y plus g. The function g2 with r2 to r2 given by g2 xy is equal to xy comma x squared by 2. Okay. So these are the situations in which. So now the question is that we need to find which one is the proper map. So remember, what does a proper map mean? If suppose we have map from x to y, suppose we have map from x to y, and suppose C is a compact source of y, then F inverse is compact. So that is what by we make proper. Okay, now we need to show that which of these function, which of the following function proper. So for that, So, so, uh, so firstly, okay, before explaining the answer is for the answer is option C, option E, option. Okay. Now the question is, so the for option A and B, the inverse image of closed 0, 1 is not compatible. For option C, since polynomials are compact, polynomials are continuous, of course, polynomials are continuous. Since polynomials are continuous, so inverse image of a closed set is closed. So it is enough to show that the inverse image of a bounded bounded. Now note that if is any non-constant polynomial, then we have what? Mod fa goes to infinity as mod a goes to infinity. So inverse image of a bounded subset of R under F is bounded in R. So please go through the argument. So let me repeat the argument. So for option A and B, so for option A and B, uh, huh. So for option A and B, the inverse image of open 0, 1 is not compact. So that's why option A and B will not is out of picture. Okay. Now for option C, since the polynomial is continuous, so the inverse image of closed set is closed. So it is enough to check the inverse bounded subset is bounded. Okay. Now since f is any non-constant polynomial, then mod of fa goes to infinity as norm x goes to infinity. So the inverse bounded subset of R is bounded in R. Okay. Okay. Now for option E, since the given function is continuous, so inverse image of a closed set hence to show properness it is enough to show that So it is enough to show the inverse. Sorry, there is again some issue. Well, so inverse image of bounded is bounded. Okay. So inverse image of bounded is bounded. So consider f3 inverse minus r comma r for r greater than 0. Since f3 x comma y is equal to x4 plus y4 greater than equal to 0, we have f inverse of minus r comma r is equal to f inverse 0 comma 1. Now, since 0 less than equal to x4 plus y4 less than equal to r keeps 0 less than x4 less than equal to r and 0 less than y4 less than equal to r. So 0 less than mod r less than equal to r to the power mod x r to the power 1 by 4. Okay, and 0 less than mod y less than equal to r to the 1 by 4. So f3 inverse minus r comma r subset of minus r to the 1 by 4 comma r to the 1 by 4 cross minus r to the 1 by 4 comma r to the 1 by 4. This tells that inverse image of every bounded set is bounded. Okay, and for f is equal to, note that G is a homeomorphism with the inverse map G inverse x comma y is equal to x comma y minus q. And for option G, what will have, we have inverse image of 0 comma 0 is not bounded. Okay, is not bounded. And for option D, inverse image of 0 not bounded. Okay, so let me write down the, let me go through the whole argument. So what was the question? The question was to determine whether the given maps are proper or not. Okay, for that what we are choosing inclusion map open 0 or 30. So there are some given maps. Okay, So now the point option C, E, A for the answers. Now why the other is not the answer? So for A, B, the inverse image of closed interval 0, 1 is not compact open 0, 1. For C, since the polynomials are continuous, so the inverse image of closed set is closed. So it is enough to show that inverse image bounded is bounded. Okay. Now note that if f is non-constant polynomial, so norm x goes to infinity as not x goes to infinity. So this is the inverse image bounded subset of R under f is bounded. For E, since the given function is continuous, the inverse image of a closed set is closed. Hence, to show the properness, it is enough to show that inverse image of any bounded set is bounded. So consider f3 inverse minus R2R, since f3 of x, y, x4 plus y4 greater than or equal to 0. So f inverse third bracket minus R comma R is equal to f inverse of 0 comma R. Okay. So this says that inverse means compact set is compact, and similar argument is that for option F and G are not coming to the picture. Okay. So this is the full argument. Okay. So that's all for the objective question of assignment 5. Okay. So now let's go to the assignment 6. Assignment 7 objective. Well, kind of wait a minute. So let me check the things it is not fine or not. One minute. Hmm. Now, uh, okay. So now let's go for the assignment 7. So objective assignment 7. Okay. So wait. Hmm. Okay. So first question is as follows. Let f be a possibly there is some issue in the Google Meet. That's why sometimes the voice is breaking and sometimes okay. I mean sometimes webcam is not showing in my Google Meet. Possibly there is some internet issue in Google Meet. So let it be a filter on it. Then topology tau is equal to f union phi is the topology on it. Question is true or false. So answer is true. Why? Because can be defined as since x belongs to tau and tau is closed under finite intersection and arbitrary union. Okay. Question number two. Suppose if F1 and F2 are filtration on X, then F is equal to A intersection B, such that A belongs to F1, B belongs to F2, is a filter on X. So it is also false. Why? Put X equal to A comma B, F1 is equal to A comma X, F2 is equal to B comma X. Then the corresponding intersection is empty. Okay. So well, just one more thing is that here in this filter thing, it is not really difficult. You only need to go along with your definitions. Okay, definition, lemma, theorems, all those things. It is not. I mean, it is not difficult at all. Okay. Now, question number three. Question number three is let capital X be a set having at least two elements. If B is a base for filter F, then every element of it can be written as union of members of it. Answer is false. Question is why? Why such a situation is not possible? Because let A comma B belongs to capital X and let F is equal to A comma X and B is equal to A. Then of course B is a basis for it, but X will be written as union of members of B. Okay. So what happens here is the following. Suppose we have subject false. So we take two elements A, B, and X, and so we choose a filter F with singleton A, comma capital X, and B is equal to doubleton A, singleton A. Then B is a base for X, where X cannot be written as the union of members of B. Okay. Now the next question. Let X be a set having at least three elements and let AB belongs to it, then the filter generated by the subbase yes x mod singleton A, comma AB contains exactly four elements. Okay. Now how this can be done? So we need to find four elements. What are the possible options? So the subbase is generated by these four elements: x minus singleton A, x minus singleton B, x minus singleton AB, and okay. Now okay. So this is true. Now question of 5. So well, in this previous question there is nothing actually. We just these four elements of generate the subbase. That's all. There is nothing to do actually. So let capital X be a topological space and let F be filter on X such that every cluster point is a limit point of it. Then F is an ultra filter. How? So for this type of question, so for solving this type of question, what you need to do? You need to keep in mind the all possible you need to keep in mind the definitions of filters, ultra filters, and all. Okay. Now, if you go through the, now if you go now if you go through a definition, you will find that it is also false. Why? Because take x equal to the set of natural numbers if the cofinite filter on x, then for any x belongs to x, we have nx is equal to x minus a union x squared is finite, and since nx subset of x this tells that x converges to x, and so f converges to every point of x, but f is not ultra filter. on X since neither the state of even numbers nor the state of odd is right. Okay, so it's an ultra filter. Now please go through the argument and let me know, do you have any question or confusion in the argument itself. I shall wait for a few minutes. Well, now the next question. Question number 6. What's that? Let x comma tau be a topological space which is not indiscrete.
Hello, sir. Can you repeat the previous one?
Yeah. Tell me. Yeah, tell me. Hello.
Can you repeat the previous one?
Yeah, sure, sure, sure. Yes. So the 1 minute. So the previous question is that suppose X is a topological space, uh, and if we are filtered on X, then we need to show that it's such that every cluster point is a limit point of F. Then we need to show that F is the ultra filter. So basically, Mustaf Singh. So I mean, this problem has nothing to do with except constant definitions. Okay. So of course, this one might guess is false. So for in order to prove this, we need to consider counter argument. So here the counter argument that I took is the following: we take x to be the set of natural number, f to be cofinite filters on x. Then for any x belongs to x, we can choose a neighborhood nx which contains x minus a union x, or is a finite set. Then clearly that set nx subset is a filter. This tells that f converges to x, and so f converges every cluster point of x. But f is not ultra filter, since neither of the set of or even the numbers nor the set of odd numbers is in f. So that's why ultra filter or might not be filter might not be ultra filter in this particular circumstances also. So basically you need to play with the definition. There is nothing more than that. Do you understand?
Yes.
Oh, do you have any more questions?
No.
Oh, okay. So let's go back to original business. Uh, so now So the question which is going to for suppose the extra topology space which is not in discrete topology, then there exists a filter if on X such that every element of X is a cluster point of X. So every element of X is a cluster point of X. Okay, this is one statement. And second statement is that there exists a point in X which is not a limit of X. So, so how to deal with this problem? So extra topological space and which is not in discrete, we need to show there exists a filter on X and every element of X is the cluster point of X, and there is the point which is not a limit of X. So the answer is true. How it is true? Why? Take F to be singular. Then for all alpha belongs to U belongs to N of alpha, but U does not belong to X. Whereas U intersection X equal to U not equal to phi. Okay, so this is the argument. Okay, and that's all. So it is not complicated at all. Okay, so these are the question of the assignment 7 object part. So now let's go back to the subjective part solution. So let's start with the subjective question. Subjective as an inquiry. So tell me till now, do you have any question or any doubt regarding this problem, solve problem, or any question, any doubt regarding some previous problems? Let me know. I shall wait for 2-3 minutes. Please let me know. Do you have any question or doubt? I shall wait for 2-3 minutes.
Hello, sir.
Yeah, tell me, sir.
Can you repeat? Actually, I have a doubt in the previous question, one of previous question. The
Yes.
number of closed
Uh,
sub-algebras of R3
mm-hmm.
that are one-dimensional subspace.
Okay, 1 minute. Let me open the question itself. Okay, 1 minute. Hmm. So, uh, so in the screen, the question itself, right? Now, uh, so here you need to consider two. You need to consider sub-algebra. You need to also consider the subspace also, one dimensional. Okay, since it's one dimensional, so it must have a basis, right? This is a one observation. So suppose ABC is its basis. Okay. Now the algebra condition gives that ABC whole square is equal to A square B square C square. Okay. But since the base is so this A square B square C square is a linear multiple of ABC. Okay. So this implies what? A square. So A square equal lambda B square lambda C square lambda. So now we need to now then we are checking that for different ABC, how for different value of ABCs, whether one can be zero. Suppose two are zero, another is zero or not. Suppose two are equal, then whatever other. In this way, we are getting that there are total 7 possible bases. Okay, so that's why the one dimensional subalgebra R3 is only 7. There are two things to it. One is subalgebra. That's why we can say that this ABC whole square equal to A square B square C square. Secondly, since it's a one dimensional, so ABC is the basis, and so we are using the ABC whole square lambda to the ABC. Now then we are comparing these two equations and finding all possible bases. Okay, so this is the technique. Okay, there is nothing complicated, I guess. You understand? So do you understand?
Yes, yes, I understand.
Okay. Do you have any more questions?
No, 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 you got it.
Okay. What? Okay. So now, okay, let me find the questions here. Uh, well, so now let's start with. Well, so now let's start with the in the subjective type of question. Okay, of the science. Right. However, well, so now the next question is as follows. So the first question is the following. Let capital X be locally compact Hausdorff space. Let eta comma y be a compactification of x such that y minus x is a singleton set and y is Hausdorff. Then prove that eta comma y is equivalent to 1 point compactification of x. So, how to approach this type of problem? Uh, so, what we are given? We are given x a locally compact Hausdorff. Eta comma y is a compactification of x or the y minus singleton set. Y. We need to prove the eta comma is equivalent to 1 point compactification of x. Okay. So for that, what we need? Okay, so it seems it is complicated for fellows also. So the solution goes as follows. Okay, let I comma x union infinity be 1 point commodification of it. Let y is equal to x union singular t. To define f from x union infinity to y by f of z is equal to eta of z if eta belongs to x and p if p is equal to infinity. Okay. Now clearly f is a bijection f composite is equal to eta. Now if we prove f is continuous, then f being continuous from a compact space it will become homeomorphism. Okay, and this implies what? And this tells and this tells f will be in equivalence. Okay. Now, now, okay. So, uh, so F will be an equivalence. Okay. Now, for continuity of F, let Z belongs to X. So, for continuity, let Z belongs to X. Okay. And V subset of Y is open, and V contains F of Z, which is equal to eta of Z. Then, Q1 is equal to V minus singleton P is eta. Now, since eta x to eta x is an homeomorphism, so U is equal to eta upper inverse of Q1 is also an open set in X, and hence open in X union infinity containing this. Moreover, f of U is equal to eta of U is equal to Q1 subset of U. Therefore, f is continuous at set. Now, let Z equal to infinity and let V be an open set in Y containing f of infinity equal to P. Then Y minus V is equal to K1 is a closed subset of Y, and hence compact set in beta of X. So, K is equal to eta inverse of K1 is a compact set in X, and this tells that X union infinite after compactification is also same. Then the technique is that if we put U is equal to X union this infinity, minus K is an open set in X union infinity contain infinity such that f of a subset of T. Therefore, f is continuous at infinity also. So, okay. So this is the argument. Now let me know, do you have any question or doubt? I shall wait for 2 minutes. So basically, if you look at the problem, so this problem has nothing to. I mean, this problem is quite. This problem is quite easy. Okay, so hmm. So basically, you need to start with the different type of situation. So suppose the map is given to be y. Okay, so here initially we have, so initially what? So initially we have some x equal to y union p, okay, and we have already given some compactification, correct? Now we can use the compactification to make some new kind of maps, right? Now we can use that map in order to define that. In order to define the whether the given, we're getting making a new function with f, and then we are looking that, and then we are trying to show that if it's continuous and if satisfies all those conditions or not. Okay, so there is nothing complicated here. Of course, the proof is final proof is quite tricky. That I agree, but except the proof, the rest of the things are not that much difficult. Okay. Now, okay. So now go back to the next question, namely, okay. So now the kindly wait a minute. Well, so now the next question is as follows. So now question is give an example of a house drop space. Give an example of house drop space whose one point compactification is not house drop. And of course, one has to justify the answer. Okay. Now, wait. Let me have a glass of water. So how it's possible? So consider the space. So consider the space 0, comma 0 u there, 0, comma infinity cross r. Okay, as a source bar. Now then, x is house drop. However, x is not locally compact since there exists no open neighborhood V of 0, 0 such that V closure is compact, and hence in the one point compactification x union infinity of x, we see 0, 0 and infinity can't be separated by open sets. Okay, so basically what we have done. So we have some x and then x is house drop, but x is a locally compact house drop. See, there we have some open neighborhood V of 0, comma 0 such that V closure is compact. Okay, and we are using this compactness of the situation. So V is called. Hence, the one by compactification of x in infinity of x, we see that 0, comma 0 infinity cannot be separated by open sets. Okay, so that is the argument. Now, take x be any one by compactification of R. Given x belongs to x minus 1, show that every neighborhood u of x in x has the property that u intersection r is unbounded. How to solve? Now, so for this, what we need to do? So suppose here exists x belongs to x minus r and the neighborhood u of x in x such that u intersection r is bounded. Then we can choose a natural n greater than 0 such that u intersection r can be put as outside of minus n comma n. Now since v is equal to x minus n comma n is open in x, so it follows that u intersection v is a neighborhood of x, which is disjoint from r. So this tells what? This tells that x not in closure of r, which contradicting what? Contradicting the fact that r is equal to x. Okay. So this is the argument. So basically, so let me repeat the argument. So x is here one by compactification of r. Okay, and suppose we choose a point x and x minus y. Then what we should do? Then the question is to show that every neighborhood u of x in x has a property that u intersection r is unbounded. For that, what we take a x in x minus and a neighborhood u of x in x. Okay, such that u intersection x, u intersection r is unbounded. Then we can choose a natural number n greater than 0 such that we can choose a natural n greater than 0 so the u intersection r is subset of n minus n. Okay, now since v is equal to x minus n minus n comma open x, it follows the u intersection v is the neighborhood of x and which is disjoint from r. This tells that x does not belong to r closure, which is contrary to the fact that r is dense in x. Okay, so this is the argument. Now, so I hope this argument is clear to you. I mean, it is not complicated. You just need to write down the argument line by line. Also, you will get what is actually happening, because there is nothing really magic here happening. Okay. Now, the next question. Let f belongs to C01 and put a minus 0 to 1 f x and x to the power n gs. Okay. For n is equal to 0, 1, 2, and m of f is equal to a1 of f, m2 of f, m3 of f, dot, dot, dot. Show that m is injective on C01. How to do? For each n, the function mn from C01 to R is a linear map of vector spaces. And so, yeah, from C01 to R, n growing with is of course a linear map. Okay, there is nothing complicated until now. So, so to to show that, to show injective, it is sufficient to show that if mf is equal to 0, 0, 0, 0, 0, then this implies f equal to 0 in C01, right? So of course it is, this is what what one means injective, right? Now let mf, that is the integration is 0, 0, 0, that is mf is integration 0 to 1 fn x to the power n dx equal to 0 for all n. Okay, this implies for every polynomial px in the 0 to 1 fx dx dx. Now the trick comes here. Now the trick comes here by, with stress, approximation test. Theoretical polynomials px converging uniformly to f101, then integration 0 to 1 fx whole square dx is equal to integration 0 to 1 fx is the limit n tending to infinity pnx, which is nothing but limit n tending to infinity integration 0 to 1 fx pnx. This is 0. Okay, but what we are getting, but we are then getting that, but fx square greater than 0 for all x in 0 comma 1 and f continuous. So this implies what? Fx equal to 0 for all x. So this answer. So let me repeat the whole thing. Okay, before that, let me have a glass of water. Ah well. So let me repeat the argument. So we have some math, some linear map A and F, which is integration 0 to 1. Integration 0 to 1. Okay. Now what we're doing is the following. So to show if it's injective, we have sufficient to MF equal to 0. Okay. So we start now with MF equal to 0. And this implies what? Integration 0 to 1 if fx into x cube and dx equal to 0. This implies what? For every polynomial of px integration 0 to 1 fx px gx. Correct. And the trick is the following. By Wistar approximate test, rearrange the sequence of formula p and convert uniformly to a form 0 1. Then integration 0 to 1 fx whole square dx into 0 to 1 fx into limit intended p and x dx. This implies what? Limit intended infinity is 0 to 1 fx into p and x 0. But since f is greater than 0 and f greater than that's fx, so this problem is extremely important for not only for this topology but for possible this type of problem comes in the computer exams like JAM, NET, and even in any PhD comprehensive exam, this type of question comes. Okay, so uh, okay, kind of I shall get back for 2 minutes. Okay, so these type of problems are extremely important in different entrance exam, computer exams also. Okay, so that's why you should practice this type of problems as much as you can. Then only you can have a hands-on on this type of problem solving. And after all, just keep in mind, after all, the knowledge is not that important. It is also important that you practice the knowledge so that in exams, in computer exams, and in those type of situations, you can immediately solve the problem. Okay, so make sure of practicing this type of problems soon. Okay, So now let's go to the next question. Let, yeah, x to y be a continuous map of metric space. Show that the following. One is if f is a proper map, then f is a closed one. Second, if f is a proper bijection, then f is a homeomorphic. Okay, so there are two. Suppose if it's continuous, a metric space. If it's a proper, if it's closed map, if it's a proper bijection. How to do? Let f is a closed subset of f. Let y be a point of y, which is in the closure of f. We want to show that y belongs to f of s. There is a sequence xn in f set. Y is equal to f of xn plus y. Now, since y is equal to yn, what is this? Now, since y is equal to yn, union y, this thing is compact. Since this thing is compact, so properness of A implies if inverse F is compact. Subset of X. And since X subset of F inverse of S, there exists a subsequent X and K converging to J. And since Xn subset of F and F is closed, it follows that J belongs to. But then f of z is equal to limit f of x and k is equal to limit xn is equal to y. So these implies y belongs to f of f as desired. Okay. So this is the argument. Well, this argument nothing complicated. This argument, okay. So basically, what we have done. So through the first. So first option is that so there is a sequence fn in f such that yn equal to fxn and this f of xn goes to y. Now since now since s is equal to y, n union y, the compact and proper of subspace of f, this implies f inverse a compact subset. Now since this sequence xn subset of f inverse A, so there exists a subsequence x and k converging to Z. Now since xn subset of f and f is closed and follows that Z belongs to f. But then it follows that f of z is equal to limit f of x and k, which is nothing but limit of f of x and y. And this implies that y belongs to f of x as desired. Okay. So this is the argument. So yeah. So this is the argument that's desired. Okay. I mean, so basically we have used some technique. We have used nothing extra here. Okay. And for the next part, what I do, since uh, continuous bijection which is closed is the homeomorphism. So by part 1 we are getting 2 directly. So basically that is the thing. There is okay. So using part 1, this part 2 we are getting okay. So basically solving these problems require a significant amount of practicing. Okay. So do practice a lot of this type of problems so that you can get a grasp of how to attack this type of problem. Okay. Now, well, so 1 minute. Yeah. So that's all for today. In the next session, we shall start solving the rest um, assignments. Okay. So if you have any doubt or any question, please